Good day once again, everybody. And we are looking at question 5 now, based on rates of chemical reactions from the June 2022 exam paper. So if you haven't subscribed, please just make sure that you're part of the family. And of course, you can get in touch with us if you need any assistance with mathematics or physical science. Our email address is info@mlungisinkosi.co.za. And please look out very soon. Our website will be coming up and we'll give further details about that. And of course, after you finished watching this lesson, you can just go and hit that like button, okay? And please just share and tell as many people as possible that, hey, you've got your favorite plug right here from your favorite uncle. And then also at the end of the lesson, please just give a super thanks, tell your parents to just make a monetary contribution that will help us to further our goals and make sure that we continue producing this wonderful content. All right, so let's have a look at the question. So they say learners use the reaction of magnesium carbonate with excess dilute hydrochloric acid. So we need to note that so the magnesium carbonate, in this case, it means that would be the limiting reagent. Why? Because the hydrochloric acid is in excess, right? So they say to investigate the relationship between temperature and the rate of chemical reaction. So they give us the balanced equation there for this reaction, and they also give us the graph. Okay, note that this is the graph of average rate of production of carbon dioxide, right? So it means that we are looking at the rate of production of carbon dioxide. Keep that in mind. So they say define the term reaction rate. So remember that we say reaction rate, this is the change in the amount of products or reactants used or products produced, in this case, per unit time. Okay, so you can say this is the change in concentration of the products per unit time, or you can say change in concentration of the reactants used per unit time. Okay, right, now they say state two conditions that must be kept constant during this investigation. Now note that already we know that we are varying temperature, right? So we can choose any of the the other factors. We can keep the concentration, so I can say, well, the concentration of hydrochloric acid, right? And in this case, another factor that I would need to keep constant. Remember, the only thing that I keep varying is temperature. You can say the mass of the calcium. Is it calcium? Magnesium carbonate, rather. Okay, so the mass of magnesium carbonate. Okay, you can also talk about in this case the other factor. You'd say maybe the surface area of magnesium carbonate. Okay, right, so those would be the two factors that I can think of. Okay, right, now they say use the collision theory to explain the relationship shown in the graph. Now I want you to note that as temperature increases, okay, note what's happening to the average rate of production. So in this case, we see that as temperature increases, so does the rate of the reaction. Now they say to us, we should explain that according to the collision theory. Remember, an increase in temperature, okay, and if you don't know what we are talking about, it means you haven't watched our video on rates of reactions. Please go and do that. Go to our playlists and look at rate of reaction. So first of all, we say an increase in temperature will increase in this case the average kinetic energy. So average Okay, I'm trying to fit that in there. So this would be the average kinetic energy. Okay, right? So what does that mean? It means now more reactants have sufficient kinetic energy. More reactants have sufficient kinetic energy. Have sufficient kinetic energy. Have sufficient EK. And in this case, that will lead to an increase in the rate of the reaction. Okay, so more so we said an increase in the amount of in temperature will increase the average kinetic energy. So now more reactants have sufficient kinetic energy that will result in more collisions per second, more effective collisions per second, effective collisions per second. And sorry about that bad handwriting. More effective collisions per second, and so that will increase the rate of the reaction. Okay, right. And that will increase the rate of reaction. So that is the explanation. So whenever we increase temperature, we are increasing the average kinetic energy. So now it means that more reactants will have sufficient kinetic energy, so that will increase in this case the number of collisions, effective collisions per second, and that will in turn increase the rate of reaction. Okay, right, now moving to the next one. They say the learners obtained the graph above using 5 grams of magnesium carbonate, okay, with excess hydrochloric acid. So we know we are now going to use 5 grams of magnesium carbonate. And of course, I'm expecting that would decrease as, the reaction takes place. Remember, they did say that we've got magnesium carbonate in this case, and the hydrochloric acid is in excess. Okay, now, all right, so notice that they have formed this reaction at 40 degrees. Okay, so they want to know the time taken for the reaction to run to completion. Now, I want us to please just pay attention. So we've got the rate of reaction. Let's find first of all the rate of reaction at 40 degrees. So if we follow the vertical line there, you'd see that at 40, our average rate of reaction in this case is 0.5. Okay, so in this case we've got the average rate of reaction, okay, and it's in grams per minute. Okay, so that means in this case, given that we've got magnesium carbonate, is it possible for us to determine the amount of carbon dioxide that we will be able to obtain on the other side? Okay, so I'd say, well, with the 5 grams of magnesium carbonate, so number of moles, that's going to be mass divided by molar mass. We've got 5 grams. Now remember, for magnesium carbonate, we would have to look at our periodic table, right? So we would say, all right, okay, let me just open my periodic table over here. So with magnesium, magnesium is 24. So this is 24 plus carbon, which is 12, plus 3 times 16. Okay. I should have my calculator somewhere there. Okay. Right. So, all right. So we're going to say 5 divided by, I'm going to just put that in brackets. So that's 24 plus 12 plus 3 times 16. I get a value of 0.06. So it means that we've got an amount of 0.06 moles of magnesium carbonate. So let me just annotate that there. So that's the number of moles of magnesium carbonate. But now I want you to please note, in this case, for every 1 mole of magnesium carbonate, we also get 1 mole of carbon dioxide. So it means that the number of moles of carbon dioxide will actually be 0.06. So which means number of moles of CO2 will also be 0.06, okay, moles, right? And why? Because the ratio is 1:1, right? Now I'm scrambling for space here, just trying to show how we'll be able to obtain that. Sorry if it looks a little bit clumsy. In fact, I would have actually taken some more time, so that I can some more space rather. So now that we've got 0.06 moles of carbon dioxide, would it be possible for us to obtain the mass? Okay, I'll show you where I'm going with that. So with the number of moles, can I get the mass? I'm going to write it over here on the left hand side. Number of moles is mass divided by molar mass. Okay, so the mass would be, the number of moles is 0.06 multiplied by the molar mass of carbon dioxide. Once again, go to your periodic table. Carbon is 12 plus, not multiplied by, but plus in this case. So this is plus carbon dioxide with 2 oxygens, 2 times 16. Okay. So if we multiply that number multiplied by, okay, so let's delete that. So say equal to, so that's multiplied by, we said that is going to be carbon, which is 12 plus 16 times 2, and I get a value of 2.62. Okay, so it means that the mass of carbon dioxide is 2.62, right? Yeah, 2.62 grams. Now, this is the mass of carbon dioxide that was obtained. So in this case, remember we are looking for time. So I'm going to say the average rate of reaction. So we can say rate of reaction, it's the change in mass divided by the change in time. Okay. Now, as I said, I'm scrambling for space here. I'm just going to continue over there. So change in mass. Remember, my rate of reaction is 0.5 at 40 degrees, right? In this case, remember my mass, it's mass final, which is what? Which we just got 2.62. Mass initial was 0 divided by time final minus 0 again. Okay, and all you simply do is just to cross multiply. If I divide that by 1, so it means that TF would be 2.62 divided by 0.5. So it means that the time would actually be, if I divide that by 0.5, I get 5.24. So it means that it's 5.24 minutes. Remember that the average rate of reaction was given in grams per minute. So that's why I had to use mass here, grams divided by minutes. And in this case, we said we obtained a time of what was that value that we got there? 5.23. Okay, that value that we got at the bottom there, 5.24 that's in minutes. And for some reason, I just wrote it in a very clumsy way, right? So that would be 5.24 minutes. Okay, right. I hope that makes sense. All right, now let's go to the next question. So I'm going to try and just make some space here. Okay, so now they say to us calculate the molar gas volume of 40 degrees, at 40 degrees rather, if 1.5 cubic decimeters of carbon dioxide is collected, right? So remember that number of moles in this case, we're looking for the molar volume, is volume divided by the molar volume, right? So we already have the number of moles of carbon dioxide from the previous question. We got that to be 0.06. The volume, they said, is 1.5, and we wanted the molar volume, and so obviously cross multiplying, you get 0.06 Vm is equal to 1.5. Okay, right, so we can divide both sides by 0.06. Okay, and in this case our Vm value is 1.5 divided by 0.06, and I get 25. So it means that the molar gas volume Vm for this question here, so molar volume is 25 cubic decimeters per mole. Okay, and that is how the cookie crumbles. Hopefully, ladies and gents, you were able to follow on in what I did there. Okay, and of course, if there are any questions, you can just throw them on the comment section, and of course I'll always try to answer your questions. Right, now the next question, they say to us, the graph below represents the Maxwell-Boltzmann distribution for carbon dioxide. They say redraw the graph above in the answer book and clearly label the curve as A. Right, and on the same set of axes, calculate the curve that will be obtained for the carbon dioxide at 20 degrees. Now remember that when we've got a lesser temperature, okay, so first of all, we know our distribution will be much higher. In this case, I'm just trying to redraw this. So we know that our distribution will be much higher at lower temperature, but it also means that, so I'm expecting a graph that looks something like this. Okay. You note that the average has leaned more to the left. So in fact, let me just show this nicely. So it means that the average would now lean more towards the left at lower temperature. So, okay, something like this, where you've got your average kinetic energy being lower than the average kinetic energy of graph A. So this would be graph B that occurs at a lesser temperature. All right. Please just keep this in mind. And of course, once again, you can go and look at our playlist on rates of reactions, and you should be able to get that information. All right. Ladies and gents, please don't forget to subscribe. Please don't forget to like and share, and also to use those super thanks, just to say thank you to Uncle. All right. And otherwise, I'll see you guys next time. Sharp, sharp.